Hello. In this video, we are going to look at the part 2 of the exciting series on MOSFETs. Please don't forget to subscribe and like the video. Okay, so as a designer, when you draw out your circuit before sending it to the fabrication center, you have the ability to change the length and the width of the circuit. The MOSFET on the chip. So as earlier on discussed, the width is given by this dimension and the length of the channel is also given by L as shown. This is the thickness of the oxide, which is denoted by TOX. Unfortunately, as a designer, you have no control over TOX. Typically, very small value, around 18 times 10 raised to the power negative 10 thereof. So we are going to see the effect of the length and the width on things like the drain current. First, we'll look at it intuitively before we derive an equation for the drain current to see if it confirms our intuition. So intuitively, we look at the length. Increasing the length means we are increasing the resistance between the source and the drain. An increasing resistance, we expect current to reduce. So typically, we'll expect that if the channel length is increased, then the current would be reduced, as we can see in the graph. Also, similarly, if we had a graph of um, drain current against the drain voltage, we also expect something similar. Okay. What about the thickness of the oxide? Increasing the thickness of the oxide too, we expect the capacitance to reduce. And as the capacitance reduces, we also expect the charges to reduce because the capacitance and the charges are proportionally related. And with the charges reducing, that's the charges formed on the channel here. If the charges reduces, then it means that the channel becomes less conductive. And a less conductive channel means becomes more resistive and hence less current is expected to flow. And finally, we look at the effect of the width. So if the length remains constant and we increase the width, indirectly the width becomes a function of the area of the capacitor. And we know how the capacitance is related to the area. Increasing the area means the capacitance would increase, and that means that the charges would also increase. An increase in charge, just as we already said before, means less resistance and then more current. So just as we expect to see, when we increase the width, we are going to end up getting more current. Similarly to diodes and BJTs, increasing the area of the width, or like assuming you double the area of the width, is similar to connecting two MOSFETs in parallel. What we have to look at is how increasing the area of the width could also affect the speed of the circuit. That's something we will look at into detail when we do frequency response. But for now, we will see it as a trade-off between high capacitance and speed. That's trying to get more current with high capacitance, but that also trades off the speed of the circuit. Now, before we derive equations, we should try and understand something basic here, which is very important in what we are doing. Assuming this is the source and this is the drain, if a voltage VD is applied at the drain, then the potential of the drain is higher than the potential of the source, because we expect the source to be at ground potential, say 0 volts. Now, assuming I have 7 or 5 volts or 2 volts here, then from the drain to the source, the potential should not be the same. We already discussed how the channel creates some form of resistance. So with current flowing through a length of resistance, the potential at each point will be different. For example, I expect the potential at the middle here to be 1 volt, assuming a current or voltage of 1 volt would have dropped during the first half of the journey. And during the second half of the journey, I expect all the voltage to be dropped, so the voltage here becomes 0. Okay, this leads to something very interesting. Then how does that affect the charges? We know charges are related by Q is equal to CV, where V will be the potential difference across the two plates. So assuming we have 1.5 1.7 volts here, then it means the potential difference between the source or a point near the source and the gate would be 1.7, which means there will be a lot of charges at this point. But what happens to the number of charges as we move closer to the drain? As we move closer to the drain, the potential difference between the drain, okay, let me just use something bigger here, 2.7, so I don't jump into things I don't want to mention now. Okay, so at this point, the potential difference between the gate and the drain, or between this side, is now 0.7. Remember the charge equation, which says Q is equal to CV. So the V at this point is 2.7, but the V at this point is 0.7. So I expect to have more charges compared to this side. So plotting a graph of charges, then as the potential increases, so here at the source I have a potential of 0, and at the drain I have a potential equal to VD. Now as the potential increases, then the charges will also reduce, because at this point the voltage across the capacitance, so this being the gate, so if I draw the gate here, and the source to the drain, then the potential difference across this side will be the same as the gate voltage, which I just put 2.7 there. And that means I'm going to get more charges. So this is Q. But as I move towards the drain, which has a potential of 2 volts, Then the difference between the gate voltage and the drain voltage will be 2.7 minus 2, which is 0.7. And that means that the voltage across the capacitor will be only 0.7. So I expect to have less charges according to this relation. So the charge profile will look something like this. Okay, so we are going to use this to derive an equation for ID in the next video, just to keep this one short. Thank you and have a nice time.